Jai Hind everyone. So today we are going to discuss the diode application, and in this lecture we are going to discuss the first diode application, that is the PN junction diode as a rectifier. We know that when we have the PN junction diode, how do we get that PN junction diode? It is basically consisting of the two PN junction diode consisting of two types of material, that is P-type and N-type semiconductor material. When we join these two materials, then under no bias condition, due to the concentration gradient, electrons from the N-type of material and holes from the P-type of material cross the junction. So as these charge carriers, majority charge carriers cross the junctions, then just adjacent to the junction, there is electron hole pair recombination takes place. So these mobile charge carriers will replaced by the immobile ions. So the just adjacent towards the P type of material, the majority charge carriers are replaced by the negative immobile ions, and at the end side it is replaced by the positive immobile ions. So once these and this is called as the barrier potential, and once this barrier potential or the depletion layer form, it stops further diffusion of the charge carrier across the junction. And if we forward bias this PN junction diode, then in the ideal condition, during the forward bias condition, this PN junction diode offers the zero resistance. So it acts as short circuit. So because it offers the zero resistance. So ideally this value is zero, but practically forward resistance of the diode is of the order of few tens of ohms. Whereas during the reverse bias condition, when we connect this diode, anode of the diode to the negative terminal of the battery and cathode of the diode to the positive terminal of the battery, then diode is reverse bias, and under the ideal conditions it offers the infinite resistance. So that means it will be open circuit. So we can say under reverse bias condition, diode, ideally diode is in open circuit state, and in the forward bias condition it behaves as a short circuit. So using this basic fundamental, we will explain the various types of the rectifiers. So starting with the half wave rectifier. So rectifiers are basically categorized into the two categories. One is the half wave rectifier and second is the full wave rectifier. Full wave rectifier again classified into two categories, that is sinter type full wave rectifier and bridge rectifier. So today we are going to discuss the working of all the three types of the rectifiers, and also we compare these two rectifier circuits, and the parameters will be compared in the later stage. So this is the diagram of the half wave rectifier. It is consisting of two components, that is the diode and a resistance. So when we apply the input signal, the sinusoidal input signal towards at the input terminal of the rectifier, half wave rectifier, let us understand how does it work. So during the positive half cycle, that is during the time period 0 to t/2, your diode is, the terminal A will be at positive potential and terminal B will be at negative potential. So this makes our diode forward bias. So as soon as your diode will be forward bias, it offers zero resistance, that means short circuit. And because it is offering zero resistance, that means no voltage drop will take place across this resistance. And if we write KVL in this loop, then we can say that VI minus V naught is equal to 0. That means V naught is equal to Vi. So we can say that during the time period 0 to T1, we get the, at every instant of time, we are going to get the voltage what we are applying at the input terminal. So we can say this is our output. Now coming to the negative half cycle, T by 2 to T time period. So during the time period T by T2 to T time period, terminal A will be at the negative potential and B will be at positive potential. So this negative will make diode open circuit. It will offer you infinite resistance. That means diode will be in open circuit state, and if it is open, the current will be equal to 0. So if no current is flowing through this resistance, then output will be equal to 0. So V naught will be equal to 0 during the time period T by 2 to T. So here we get the output 0. Then again for the next half cycle, again we get the output. So here we can see that during the half cycle, during the one half cycle, we are going to get the output, whereas in the next half cycle, the diode, the output waveform will be 0. So it is, you can say that negative half cycle is clipped off. So we can say this is another name of this half wave rectifier is the negative clipper. Now, if we suppose we change the direction of the diode in the circuit, let us say we reverse the direction, then during the positive half cycle, the terminal A will be at the positive potential and B will be at negative potential, and this makes your diode reverse bias. So diode is open circuit, and if diode is open circuit, then your output will be equal to 0. Here the output will be 0. Now during the negative half cycle, this terminal A will be at negative potential and B will be at positive potential. So this makes your diode forward bias, that means short circuit. And if diode is in a short circuit state, then the output will be equal to, so minus of Vi is equal to V naught. So V naught is equal to minus of Vi. That means we are going to get the output equal to 0. So here we can see that by changing the orientation of the diode or flipping the diode, the direction of the current across the load resistance also get changed. So here we are going to clip off the positive half cycle, and this is the another name of this type of half wave rectifier is positive clipper, because in this case the positive half cycle has been clipped off. So the peak inverse voltage of the diode in the half wave rectifier is Vm. Because what is peak inverse voltage? Peak inverse voltage is defined as the maximum reverse voltage that a diode can withstand during the reverse bias condition. That means up to, if a diode is having the peak inverse voltage Vm, then up to Vm the diode is in a safe condition. But if we are applying the voltage beyond Vm, then the breakdown takes place. So it is a very important parameter in case of the rectifier circuit. So peak inverse voltage in half wave rectifier is Vm. Next circuit is the full wave rectifier. So full wave rectifier is categorized into two categories. One is the center tapped full wave rectifier and second is the bridge rectifier. So first of all, we are going to discuss the center tapped full wave rectifier. So here, as the name says, it is having a transformer which is center tapped. Center tapped means that the secondary winding is tapped at the center of the transformer, and we are having the number of windings in the first half cycle are exactly equal to the second half cycle. So whenever we apply certain input, the secondary half will be providing the both half of the secondary winding of the transformer provide you the same voltage. Suppose we are having a step down voltage which is having the peak inverse voltage, peak input voltage Vm, then at the terminal between terminal A and B, we have the signal like this, which is having maximum value Vm and peak to peak is 2 Vm, and also between the terminal B and C, again we have the signal which is having the value maximum values, peak value Vm, and the peak to peak value is 2 Vm. So across both the secondary half winding, we are having the same input signal, which is the step down voltage of whatever input signal we are applying. So there are the, we can have the various types of voltage. It can be 909, 12012. That means the peak value is 9 volt and the peak to peak is 18 volt. And for 12 volt rectifier, the peak value is 12 volt and the peak to peak value is 24 volt. So this is the this is about the center tap transformer. Now let us, and here we are having the two diodes, and it is important to note that the direction of both the diodes are same, and we are having the load resistance R between these two parallel arms. So let us understand that how does this rectifier work. So during the first half cycle, 0 to t by 2 time period, terminal A will be at positive potential, B will be at negative potential, and due to the secondary half winding input signal, again this terminal B will be at positive potential and this will be at negative potential. So this plus and minus will get cancelled out. So this will be this point, or the terminal B will be at 0 potential, and due to this positive potential at the A terminal, terminal A, diode D1 will be forward bias. That means short circuit. That is short circuit. And this negative will make diode reverse bias. That means open circuit. So here we can see the diode D1 is short circuit and diode D2 is open circuit. So because of that, no current is flowing in the second loop, whereas the first loop, the current is flowing in the clockwise direction. So here we are applying the input signal Vi. So output voltage will be, and because the current, we have taken the direction of the current in the clockwise direction, and we know that current flows from the higher potential to the lower potential. That is why the resistance across the potential across resistance will be positive, and potential across the resistance at this side will be at the negative potential, and this will be positive and this will be negative. So if I'll write the KVL across this, it is Vi minus V naught is equal to 0. So V naught is equal to Vi. That means at every instant of time, whatever input signal we are applying, the same we are going to get at the output. So when we are applying the maximum value at the input terminal, we get the, at the output, we get the maximum value. So this is how we get the output. So this is the output during the first half cycle. Whereas due to the secondary half of the secondary winding of the center tap transformer, diode D2, because it is in a reverse bias state, that means no current is flowing, and because of that no voltage will be available across this load resistance. The only voltage appearing across the load resistance is due to only the diode D1. Also, this is important to note that during the first half cycle, across this diode, if we look it carefully across this diode D2, the total voltage which is appearing across this diode is, this is the voltage Vm with this polarity, and here also we are going to get maximum voltage Vm with the polarity plus and minus. So if we look across these two terminals, if we look at from this terminal, we find that the voltage, the net voltage which is appearing across this diode is, let us say this is VD2. So if I write KVL in this loop, it will be Vm plus Vm minus VD2 is equal to 0. So VD2 is equal to 2 Vm. So the voltage, the magnitude across this voltage is 2 Vm, but because direction of the diode is like this, so the anode is connected to the negative potential and cathode is connected to the positive potential. That means the magnitude of this voltage which is appearing as this across this diode is 2 Vm, but it is a negative voltage. That means the peak inverse voltage in center tapped full wave rectifier is 2 Vm. That is the maximum reverse voltage which is appearing in the first half cycle across this diode is D2 is equal to 2 Vm. Now coming to the negative half cycle. So during the negative half cycle, that is T by 2 to T time period, terminal A will be at negative potential, B will be at positive potential, and also the secondary half of the secondary winding, terminal B will be at negative potential and C will be at positive potential. So if we look at the polarities across the diode, that makes diode D1 reverse biased, whereas diode D2 forward biased. So D2 will be short circuit and D1 will be open circuit. So because of that, your current will be flowing in this direction, because this arrow represents, this triangle represents the direction of the current in the circuit. So if your current is flowing like this, then we can see that the voltage, output voltage will be equal to, it is minus of Vi plus V0 is equal to 0. So V0 is equal to minus of Vi. So now here we can see that during the output voltage, V0 is equal to Vi. So we can see that in both the half cycle, the direction of the current across the load resistance remains same. So even though in the second half cycle, because direction is same, so we are going to get the output voltage in the same direction as it was in the previous case. And at every instant of time, whatever input signal is appearing across the secondary winding of the transformer, the same second half of the secondary winding of the transformer, the same is appearing across the load resistance RL. So this gives you the output. So here we can see that how our bidirectional current is changing into the unidirectional. So basically rectifier is a circuit which converts the AC into DC, the bidirectional current into the unidirectional, or you can say the alternating current into the direct current. But this current is actually the pulsating DC, means it is having lot many AC components are being superimposed on the DC component. So again, during the second half cycle, that is T/2 to T time period, when your diode D2 was short circuit and D1 was open circuit, again the voltage which is appearing across this voltage, maximum voltage is Vm, and here also the voltage which is applied across the first half of the secondary winding of the transformer is Vm. So if we measure the voltage which is appearing across the diode D1, that is VD1, that is equal to, this is the diode direction. So again this Vm and together with this Vm, if we add these, or if we write the KVL in this loop, so we can say that minus of Vm plus VD1 minus Vm is equal to 0. So VD1 is equal to twice of Vm. So again, this voltage is a magnitude is 2 Vm, but the polarity of this diode is negative. So that means that is the voltage during the next half cycle. During the second half cycle, whenever the voltage which is appearing across the diode D1 is equal to 2 Vm, and it is a reverse voltage. So again we can see that the maximum reverse voltage or the peak inverse voltage across in the center tap transformer is 2 Vm. So we can say that in the every half cycle, the one diode is dealing with the reverse voltage, and that is the 2 Vm. That is a maximum reverse voltage. So this is you can say the one disadvantage of the diode. Suppose we are having a diode whose specifications are Vm only, the peak inverse voltage is Vm, and if you are connecting the diode in the circuit, and across that circuit whose peak inverse voltage specification wise is Vm only, and in every 1/2 cycle the voltage which is appearing across this diode is 2 Vm, then that this is dangerous for the life of that diode, and it may get damaged very quickly. So here we can see, if we compare the half wave rectifier and the full wave rectifier, we can see that the peak inverse voltage in half wave rectifier is Vm, whereas in center tap full wave rectifier, the peak inverse voltage is twice of Vm. Whereas if we talk about the efficiency, then efficiency of the half wave full wave rectifier is almost double to that of the half wave rectifier. So here are the various parameters which can be calculated. So there are the 4 parameters which are basically we calculate. One is the RMS value, that is the root mean square value. Second is the DC value or the average value. Then the efficiency and the ripple factor. So root mean square voltage can be calculated by the formula, that is Vm square by 2 pi. And because we are talking about the half wave rectifier, so if you integrate this, So because we know that 0 to pi, the signal is appearing, whereas during the pi to 2 pi, the value is 0. So we can say this and pi to 2 pi, and this will be 0. So that's why this part is omitted, and we are having in this equation only Vm square by 2 pi, that is the base value. The base value is 0 to 2 pi for one complete cycle, and because the second part is 0, so we are only showing here 0 to pi sine square omega t d omega t. So using the cos 2 theta formula in the trigonometry, we can replace this sine square omega t by the term 1 minus of cos 2 omega t, integrating and putting the limits, we get the VRMS value, that is equal to Vm by 2. So in half wave rectifier, Vm by 2 is the root mean square value. Then the average value is what? The area under the curve divided by the base value. This will give you the average value. So here again Vm by 2 pi, again because in the second half cycle we are not we are only having your signal is only appearing for the 1/2 cycle. That is why it is we are considering only 0 to pi, and if we solve this, then the value of the RMA average value comes out Vm by pi. So now formula of the ripple factor is given by this VAC by VDC, and we can further solve this by putting the value of VAC and VDC. VAC is nothing but the VRM, because the VRMS value is what? It is having both the components, DC component as well as the AC component. So VRMS is equal to under root of VDC square by VAC square. Similarly, IRMS is equal to IDC under root of IDC square plus IAC square. So here VAC can be written as this, and if we place this value, we get this formula of the ripple factor, that is under root of VRMS square by VDC square minus 1. And this value we have already calculated. So by putting these values, we find the ripple factor, that is 1.21. Now, the power is the DC output power divided by the input power, because we are applying the AC input signal and output we are getting the DC signal. So the ratio of DC output power, DC power to the AC power gives the efficiency. So already calculated the DC value, and we have already calculated the DC value. So putting that DC value in the equation, and AC value is what? Both the resistances, the forward resistance of the diode and the load resistance, both are coming into the picture. So that is why we are having both the resistance. But because the value of RF is far less than RL, so we can neglect this value. And if you are neglecting this and putting this value, we find out the efficiency, that is 40.5%. So this is all about the parameters of half wave rectifier. In the next lecture, we will continue with the calculation of the various parameters of the full wave rectifier, comparison of the two types of rectifier, and the working of the bridge rectifier that we will be discussing in the next lecture. Thank you. Jai.